Chapter 13 homework, it goes this diagram and it says that the crane is traveling at a speed of 10 feet per second when it's brought to a sudden stop. It's asked to find the maximum horizontal distance through which the bucket will swing. So we have the two free body diagrams of here, and then whenever it's at the apex of its swing. Using conservation of energy, we can write the 1/2 mv squared plus the potential energy at this point is equal to the kinetic energy plus the potential energy at this point. We know that if we set the reference point here at the bottom, that the potential energy due to gravity is going to be 0, and that here, when it's at its max height, the potential energy, the kinetic energy, is going to be 0, so we can write that to be 0. So then we end up getting that 1/2 mv squared is equal to mgh. That's what I have written here. Solve for h, and we get that h is 1.5528, and h is that distance from the bottom to the reference point up to where the ball is now, or the crane is now. The crane bucket, is that now. So we do 30 minus the 1.5528 to get this new y, and then we just use Pythagorean theorems to find that distance x of the horizontal displacement, and that x is going to be 9.53 feet. See from the homework, here's this diagram with initial velocity 72 kilometers per hour, and then it speeds up to 108 kilometers per hour. There's a 2% grade, and it travels 300 meters. It has a mass of 1,800, the cab, and the trailer has a mass of 5,400 kilograms. So that's to find the average force of the wheels, the cab, and the average force of the coupling between the cab and the trailer. So I went ahead and converted everything to meters per second. So our first velocity is 20 meters per second, our second velocity is 30 meters per second. And then I went ahead and found the initial kinetic energy, which is 1/2 mv squared. The mass is the combined 7,200 of the cab and the trailer. So V we found to be 20 meters per second, and this is our initial kinetic energy. Our final kinetic energy is same thing here, except we changed the velocity because the velocity changed to 30 meters per second. And then I went ahead and found the work, which is going to be the F sub x, which is your frictional times your distance x minus mgh. So we get F times that distance of 300 that was given, minus m, which is 7,200 g due to gravity, 9.81, and then h, which is 300 times 0.02. And then we go ahead and apply the principle of work and energy, which is T1 plus the work is equal to T2, and went ahead and substituted those values, and you solve for F, and you get that F is equal to 7413.3 newtons, which comes out to be 7.41 kilonewtons. The second part is asking for the coupling force. So you just use a trailer alone as a free body diagram, and then you do the same thing for T1, your kinetic energy, except this time you just take out the value of the weight of the cab, or the mass of the cab, So you just include the mass of the trailer, which is 5,400. So you find your new T1s, your new kinetic energies for T1 and T2, and then same thing with finding your work done. The same formula. So that's what I went ahead and did here. So F sub c times 300 minus mgh, same thing. And then you go ahead and plug all that stuff in, and you find the coupling force, which is just going to be 5,560 newtons. And since it came out positive and we wrote it out to be in tension, it's going to be in tension. The third problem from the homework, it gives this diagram of the subway traveling to the left at 30 miles per hour. And it says, when the brakes are fully applied on the wheels of cars A, causing it to slide on the track, but they're not applied to the wheels of cars C and B, it gives the coefficient of kinetic friction is 0.35, and it asks us to find the distance required to bring the train to a stop and the force in each coupling. So I went ahead and applied the conservation of energy. So and the principle of work and energy. So we have our T1 is 1 half mv squared, and then since these are giving in the masses are giving in tons, we have to convert that over to slugs. So I went ahead and did that. This is 40 tons. This one's 50, and this one's 40. So I went ahead and converted the 40 tons, which is 8,000 pounds divided by 32.2. And you get this number as your slugs for your 40-ton one, and the same thing with 50. So your T1 is going to be 1 half mv squared, and it's the total masses of these three. So I have 2 times the slugs. I think it's 2484 slugs plus the 3105 slugs. And then your velocity is going to be 44. It says 30 miles per hour, but I went ahead and converted that to, what is that, meters per second? I mean, sorry, feet per second. Yeah, feet per second. And then you get this large number as your kinetic energy. You know that when it stops, your kinetic energy is going to be 0. And then to find your work done, it's your frictional times that distance x. And we know that friction is mu sub k times the normal force, where the normal force is nothing more than just mg. So went ahead and plugged that in. So we have our frictional force negative. It's always negative, 0.35 times 40 times 2,000 times x, or 20,000, I'm sorry. No, 2,000, yeah, 2,000. Because this is only acting on cart A, which is 40 tons. So 40 tons times 2,000, because 1 ton is 2,000 pounds. Then we apply the principle of working energy. T1 plus U is equal to T2. And we solve for that distance x, which is going to come out to be 279 feet. The second part is asking us to find the force in each coupling. So I went ahead and drew the free body diagram of cart B and C, and then with that force of the coupling in tension going out to the left. And we do the same thing, just apply principle of working energy. We find our T1. The only thing that changes now is the masses, because we took out one of the carts. So we get our T1 value. Our T2 is the same thing, is going to be 0. Our U, our work is going to be our frictional times that distance x that we found earlier here to be 279. But this time we don't know what our I'm sorry, it's not friction. It's going to be the force in the coupling to be in, that we wrote out to be in tension. So it's going to be the force from the coupling times the distance x. And so we solve for that force in the coupling, and then we have that it comes out to be a negative answer, which is negative 1,381, or negative 19,381.5 pounds. And since it came out negative, that means our sign convention that we wrote out is going to be wrong. So it's actually going to be 19.38 kips, and it's going to be in compression. All right, so this is problem 4 from the homework. It gives us that a sphere A here is given a downward velocity of v naught, a magnitude of 5 meters per second. It swings in a vertical plane. The rope has a length of 2 meters, and it has to find the angle theta at which the rope will break, knowing that it can withstand a maximum tension equal to twice the weight of the sphere. So we just go ahead and write out our kinetic energy equation, 1 half mv squared, and find that T1 is equal to 12.5 m. And then go ahead and write out our second kinetic energy at T2 is going to be 1 half mv squared. And then our work done is going to be mg. And then looking at just drawing out this triangle, this h distance is going to be 2 sine theta. So it's going to be mg, and then that h distance, like I said, is going to be 2 sine theta. So we go ahead and apply our principle of work and energy of T1 plus the work done is equal to 1 half RT2. That's what I did here. And then I just solved it in terms for v squared. So we get v squared equals 25 plus 4g sine theta. Now just looking at the free body diagram, of it having a tangential velocity and a centripetal velocity, we can write out our Newton's second law of kinetics of force equals mass times acceleration. And we have that 2 mg because that is what was given, that it can withstand a maximum tension equal to twice the weight of the sphere. So it's 2 mg minus, that's the cable, minus mg sine theta, because we're taking this direction in the x to be the positive sign convention, and we know that the gravity is just directly down, but to take it into account of this x direction is be 2 minus mg sine theta right here is equal to mass of acceleration. We know that since traveling has a acceleration due to centripetal acceleration, so we can rewrite the acceleration as v squared over r, where r is going to be our length given, which is going to be 2. And then we have this equation here, which comes to v squared equals 4g minus 2g sine theta. So since we know that v squared is equal to 4g minus 2g sine theta, we can plug that in for this v squared here and solve for theta. And we get that sine of theta is equal to 0.2419. Take the inverse of that, and we get that theta is equal to 14 degrees. This is problem 5 from the homework. It's supposed to be a chairlift, terrible drawing, but the dimensions are right, 300 and 750 meters. It's a chairlift designed to transport 1,000 skiers per hour from the base A to the summit B. The average weight of the skier is 70 kilograms. The velocity given is 75 meters per minute, and then it's asking us to find the average power required and the required capacity if the mechanical efficiency is 85% and if a 300% overload is to be allowed. So we have the equation for the average power is going to be the change in potential energy divided by the total time, or the change of time. So potential energy here is going to be due to gravity, and so that's mgh. Since it's 1,000 skiers, the total mass would be 70 times 1,000 times the gravity component, 9.81, and the height given was 300. And then that divided, since it's per hour, so divided by time in seconds, so 3,600 seconds is 1 hour. And we get that our average power is going to be 57,225 newtons times meters over second, which is going to give us a power of 57.2 kilowatt. Yeah. For B, the maximum power required, the required capacity of the motor if the mechanical efficiency is 85% and if a 300% overload is to be allowed. I first found the maximum with a 300% overload, so it's 57.2 plus 3 times 57.2, so we get the maximum power with 300% overload is going to be 229 kilowatts. But with an 85% efficiency, we just divide it by 0.85, and we get that the answer is going to be 269 kilowatts. Problem 6 from the homework. So we have this diagram here. It says a 2 kilogram collar is attached to a spring and it slides without friction. It gives us that the K constant for the spring is 600, and at point C there is no spring tension. It's undeformed. It says that if the collar is released at A with no initial velocity, determine the velocity at B and at C. So since we know that it's undeformed at point C, that means there's no elongation. At B, this distance here is 200 millimeters. This distance between at C is 150, so there's only a 50 millimeter elongation. And then A, that same logic applies. There's 100 millimeters of elongation. So at B, if we set the reference point down at the bottom and we just apply our conservation of energy, here we have potential energy due to gravity, the energy due to the spring, and kinetic energy. So at A, since it's released and with no initial velocity, that means we have no kinetic energy, and we have the potential energy due to gravity, and we also have the spring spring energy. Yeah, just gonna call it that. So we have 1/2 kx squared. This k is constant. The x is that how much it's elongated. We found out that it's 100 millimeters. 100 millimeters, which is 0.1 meters. So 1/2 kx squared plus mgh. The mass is 2 kilograms. G 9.81, and then that distance is 0.2 meters. Is equal to, and at the bottom here at B, it's going to be no potential energy due to gravity. There's going to be still a spring constant of 1/2 kx is 0.05 squared, and minus, and then plus, and then there's going to be some kind of velocity at 1/2 mv squared, but 1/2, and then the m is just 2, so I just wrote out 1v squared. Solve for v, and then we get that the velocity is going to be 2.48 meters per second going off to the left. Now we apply that same concept at C, and here I wrote it out a little bit better so I could understand it, or just read it out a little bit better. So we have our potential energy from the spring, our spring energy due to gravity, and then the kinetic energy is equal to the same stuff. But then you'll notice that at C, or at the beginning, we have the same from up here. So there is a spring energy 1/2 kx squared. Potential energy due to gravity is going to be, and at this point I sent, actually, which, to make this easier for myself, I set the reference point up at the top. So 0 plus the kinetic energy. It said that it didn't have any initial kinetic energy, so it's 0 is equal to, at here there is no spring energy because it's undeformed. Once again, since I set the reference point up at the top, there is no potential energy due to gravity, and then there's just 1/2 mv squared. We're trying to find the velocity at C. And solving the algebra, we get that the velocity at C is going to be 1.732 meters per second. 7 from the homework. It gives us this diagram, and it shows that a spring uses to stop a 50 kilogram package, which is moving down a 20-degree incline, has a constant K of 30 kilonewtons per meter, and is held by its cables that is initially compressed 50 millimeters. It says that the velocity of the package is 2 meters per second when it's 8 meters from the spring, and it's asked to find the maximum additional deformation of the spring and bringing the package to rest. So going ahead and applying the conservation of energy, at the beginning we have 1/2 mv squared, and I wrote that as 100 joules. Then we have the initial since compressed, the spring, 1/2 kx squared. That k is constant of 30 and is given, but it's actually 30 kilonewtons, so I multiply that by 10 to the third, and then there's the original compression of 0.05 squared, so that gives that 37.5 joules. And then this mgh, so we'd set the reference point down at the very, very bottom, and we have the given m, which is 50 kilograms, gravity 9.81, and then if we just drop this triangle here, given that this is 8, this angle here is 20, we get that this h distance is going to be 8 sine 20, so we get that the total energy is 1,342.09 joules. At the final position at T, down here, we have mv 1/2 mv squared. It's going to have the velocity, which is going to be 0, and then the spring constant, we don't know how much more it compresses, but we know it compresses it more from the original 0.05. So the constants stay the same, but then it's 0.05 plus this uh, additional compression x squared. And then MGH is going to be the same thing, 50 times 9.81 times x, since we don't know this distance now, sine 20. So we go ahead and apply this, and we just solve for x, and we get that the x distance is 0.269 meters. From the homework, it gives this diagram with this 10-ton truck going up a ramp of 15 degrees, initial velocity of 108, and then after 3 feet, after travel for 6 seconds, it's reduced to 36 feet per second. It's asking us to find the magnitude of the braking force and the additional time required for it to stop. So I went ahead and got the mass of the truck by dividing the 10 tons, which is 10 times 2,000 gives us 20,000. And divided by 32.2 to get the mass. And then we went ahead and drew the free body diagram of the truck on that incline surface. Using the impulse momentum principle for impulsive motion, we can go ahead and write out the M1V1 is equal to M2V2, or M1V1 plus the impulse is equal to M2V2. So that's what I went ahead and did here. So the mass, which was I found here, times the velocity is equal to the impulse, and the impulse here is going to be negative F, and then the mg is also acting in the negative direction, so plus, in parentheses, plus mg sine of 15 times that distance that it travels, which is or that time times the time, is equal to m2v2, and those are given. So we just go ahead and solve for f, and we get that our f is, which is the magnitude of the braking force, and that's going to be 2,277 pounds. And then the second part is asking us for the additional time required for the truck to stop. So we go ahead and just write out the equation again. But at this time, instead of our velocity being the velocity that was given for the second part, which was 36 feet per second, we know that when it stops it's going to be 0, so our m2v2 is going to be 0. And this time we don't know what that t value is, so we just go ahead and solve for t, and we get that our t is going to be 9 seconds. But given that it had already traveled 6 seconds, we just do 9 minus 6, and we get that additional time required for it to stop is going to be 3 seconds. This is problem 9 from the homework. So it gives this diagram, and it shows that it's shown at rest with a constant 150 Newton forces applied to the collar B, and it gives us essence to find the time in which the velocity of the collar B will be 2.5 meters to the left and the corresponding tension in the cable. So just looking at this diagram here, we know that when collar B moves 1 unit to the left, the weight A moves up 2 units. Therefore, we can write the expression of the velocity of A is equal to the velocity of B, and we can rewrite that as the velocity of B is 1/2 of the velocity of A. If we sum forces in the x direction, we get that 150 newtons minus the 2t. If we look at the free body diagram of just this collar, and then the impulse of B was going to be this times some value t. And then we just go ahead and write our impulse momentum principle for impulsive motion, which would be m1v1 plus the impulse is equal to m2v2. So we know that it starts from rest, so we have 0 plus the impulse, which was 150 minus 2t, big T, which is the tension, time to time, is equal to the m2 v2. We know that we're trying to find the time at v equals 2.5 meters per second. So we got the mass of the collar times 2.5. The mass of the collar was 8 kilograms. It's given here. And then we just go ahead and rewrite this expression as 150 T time minus 2T the tension times time is equal to 20. Now if we look at just the block A and we sum forces into Y, we can write that the T minus m2g, and then we can write it as the impulse is going to be 2T, which is the tension of the cable, minus 29.43, since this is 30 kilograms, times some time. And then we just go ahead and write once again our impulse momentum principle for impulsive motion. So we get it starts from rest, so 0 plus the impulse is equal to m2 v2, and once again our velocity is going to be 2.5 meters per second, and we get both of these expressions, and we just solve one for the other. We multiply this expression by 2 and add to the original one that we found up here, and we solve for t, and we get that the time needed is going to be 0.549 seconds. It's asking us the second part of the question to find the tension in the cable at that time, and then we simply just plug in our 0.549 into this previous equation that we found here, and we plug in our 0.549, rearrange it to we only have the big T over, and we find the tension in the cable is 56.8 newtons. Problem 10 from the homework gives us this diagram, and it says a 6 gram bullet is fired into 1 kilogram block at B, suspended at a quarter length of 2.2 meters. It swings through a maximum angle of theta of 60 degrees. It asks to find the initial speed of the bullet, the impulse imparted by the bullet on the block, and the force on the cord immediately after the impact. So we can go ahead and write, just using conservation of energy, of looking at this part of the free body diagram, of when the block, right after the block and the bullet have collided, but before it has started any kind of rise. So we can rewrite this as 1/2 of m1, or mass of the bullet plus the mass of the block, times the v squared is equal to this the potential energy due to gravity once it's at part B, which could be mgh. We can rewrite h as 2.2 minus 2.2 cosine of 60, and pull out the 2.2, and h is 2.2 times 1 minus cosine of 60. If we divide over the masses, that gets rid of it, and we end up getting 1/2 v squared is equal to gh. And here we're concerned with the velocity, so we isolate the velocity, multiply it by 2, and take the square root. So we're going to get the velocity right after it has made contact with a block is going to be 4.65 meters per second. Now we look at we're going to apply the conservation of energy again, but before and after it makes contact with this 1 kilogram block. So we have m1, mass of the bullet, times the velocity of the bullet, plus the mass of the block initially, which is at rest. Mass of the block times the velocity of the block, which is at rest initially, is equal to the total mass of the block and the bullet together, times its velocity, which is what we found here. As we alluded to earlier, this is going to be 0 because the velocity of the block initially is 0. And then the mass of the bullet was given as 6 grams, which is 0.006 kilograms. We go ahead and find that initial speed of the bullet, which is going to be 778.92 meters per second. The second part of the question is asking us to find the impulse imparted by the bullet on the block. We just go ahead and write out the impulse momentum principle for impulsive motion. So m1 v1 minus any kind of the forces times that value times that time t is equal to m2 v2. So we went ahead and found, we know these values, and we know this value as well, because this is after it has made contact with the block, and its velocity, which is 4.65. So it would be 1.006 times 4.65, and then we just go ahead and solve for that value of f of t, which is going to be 4.646 joules. The third part is asking us to find the force on the cord immediately after the impact, and then we can just sum forces in the y direction immediately after it's made impact. So we have t minus mg, and we know that acceleration at that point is going to be nothing but centripetal. So is equal, and we use kinetics here, is equal to mass times acceleration. And acceleration, because it's due to centripetal acceleration, we can really write that as v squared over r. Isolate the tension, and then solve for the tension. Plug in the knowns, and we get that our tension is 19.74 newtons. Problem 11 from the homework. It gives this diagram of 3 steel spheres of equal mass that are suspended from the ceiling. After being pulled back and released, sphere A hits sphere B, then hits sphere C. Denoted by E, the coefficient of restitution between the spheres, and by velocity, and by V naught, the velocity of A, just before it hits B. It's asking us to find the velocity of A and B immediately after the first collision. B, which is the velocities of B and C immediately after the second collision, and C, assuming how the end spheres are suspended from the ceiling. If the first sphere is pulled back and released as described above, it has to find the velocity of the last sphere after it is hit for the first time, and then use the result from part C to obtain the velocity of the last sphere when n equals 8, and the coefficient of restitution is 0.9. So if you go to write the free body diagram of the first collision between A and B, and using conservation of momentum, we can write this expression out here, which is going to be V naught is equal to this V A prime plus V B prime. The reason why there's no masses here because all the masses are the same, so we just divide one out and they all go away. And then looking at the relative velocity, we can write out the velocity of A minus the velocity of B times the coefficient of restitution is equal to this new velocity of B minus the new velocity of A. And then we can write this as the velocity of E is equal to the velocity of this new velocity of B minus the new velocity of A. We can go ahead and solve for the equations. So that's what I did here. And we get that your V of A, which is your new velocity, is equal to V naught times 1 minus E over 2. And then new velocity of B is V naught times 1 plus E over 2. So for the second collision of B and C, we just look at the free body diagram for that. And know that total momentum is conserved. And then we just go ahead and do the same thing using the results from this part. And do that, find the relative velocity once again, and then go ahead and substitute these values in to find the new velocities of C and the new velocities of B, which I found here, which is going to be V naught times 1 plus E to the squared over 4, and then the new velocity of B, once they make collisions, is going to be initial velocity times 1 minus E squared over 4. Now for n spheres, we derive the equation of V naught times 1 plus E times n minus 1 over 2 raised to the n minus 1. And then we plug in the parts for D, which is n equals 8. The coefficient of restitution is 0.9. And and we find that the velocity for n equals 8 is going to be 0.698 v naught. Alright, this is problem 12 from the homework. It gives us this diagram, and it says a 1 kilogram block B is moving with velocity of v naught of 2 meters per second, and it hits a 0.5 kilogram sphere, which is at rest. And it says that the coefficient of kinetic friction is 0.6 between the block and the horizontal surface, and that the coefficient of restitution is 0.8 between the block and the sphere. It has to find the max height, which is reached by the sphere, and the distance x traveled by the block. So to find the max height, we just have to use a conservation of energy. So it's going to be the mass of the block times the velocity plus the mass of the sphere times velocity is equal to the ending mass of the block times its new velocity plus the ending mass of the sphere plus new velocity. We know that the sphere starts from rest, so it's 0, because the velocity is 0, so that becomes 0. Mass of the block is 1, its initial velocity is 2, and then we plug in our knowns, and we get that this equation here, which is 4, is equal to the new velocity of A plus 2 times new velocity of B. So velocity, yeah. Then we write the equation for the relative velocities and solve for it, and we end up getting that negative 1.6 is equal to the new velocity of B minus the new velocity of A. And then we go ahead and solve out. Then we have two equations and two unknowns, so we go ahead and solve these equations for new velocity of A and new velocity of B. And you get that new velocity of A is 2.4 meters per second, and the new velocity of B is 0.8 meters per second. Now applying conservation of energy, we have 1/2 mv squared is equal to mgh. And then we just solve for the h, which is going to be 0.294 meters. The second part, it's asking us to find the distance traveled, and this is where we have to use the impulse. So we have, not impulse, but the work. So we have T1 plus the work is equal to T2, where the work given is by this F, which is friction, times some distance x, but friction is mu sub k times n. Mu sub k is given, and then n is the normal force of the block, which is going to be the mass of the block times gravity. So now we can rewrite this as 1/2 mv squared is equal to, or it should be plus the frictional constant, or minus, is equal to m2v2, but this is when distance traveled is the max is travel, so the end velocity is going to be 0. So I simply just move this over and then solve for x, and we get that the distance traveled is going to be 0.0544 meters, which is 54.4 millimeters.